Hello everyone. So we are going to discuss the third problem which came in BMath 2008. So the problem says that you have three complex numbers z, z square and z cube which are collinear in the complex plane, and then we have to show that z is a real number. So the problem is very easy. So let's try to solve it. So for this, there are several ways to solve this problem. So we would try to use one theorem, which we stated here. That is, suppose Z1, Z2, and Z3 be in the complex plane, then Z1, Z2, and Z3 are collinear if and only if Z1 minus Z3 divided by Z3 minus Z2 is equals to lambda, where lambda is a real number. Now, uh, in our problem, we are given that Z1, Z2, and Z3 are collinear. So why will this ratio be, real? So try to think about that. You can look at Z1 minus Z3 as the line segment from Z3 to Z1. And also Z3 minus Z2, you can look at it as the line segment from Z2 to Z3. So then the question is, uh, what can we say about the argument? So this is not very difficult to prove. So you can just simply uh, take the argument between these two lines and check it out. So if you take that these 3 points are collinear, then you can very well see that these two lines would be nothing but parallel. And so you can talk about the argument from where you can prove that lambda has to be real. So try it out on your own. I have given you enough hint. Now we would be using this theorem. So if we take z as r e to the power I theta, and then z square would be r square e to the power I theta, and z cube would be r cube e to the power, sorry, I have here e to the power I 2 theta e to the power I 3 theta. So then let's look at r e to the power I theta minus r square e to the power I 2 theta divided by uh, r square e to the power I 2 theta minus r cube e to the power I 3 theta. So let's cancel out r from the numerator and the denominator, and also e to the power I theta. So we get 1 minus r e to the power I theta divided by r e to the power I theta minus r square e to the power I 2 theta. And so this becomes equal to take out the r common. So we have r e to the power I theta. So 1 minus r e to the power I theta. And also we have 1 minus r e to the power I theta. Okay. So what we have is this ratio is coming out to be r e to the power I theta. Okay. So then there is something to note, that is, if r is equals to 0, so r is the distance of this complex number from the origin. So it's positive, but if it's equals to 0, then all of z square, z cube, and they all become the same point. And then basically, in fact, z becomes a real number. Okay, what are the other things to note is that we have cancelled this 1 minus r times e to the power I theta. So now, if r times e to the power I theta is equal to 1, then this would have become 0. So in that scenario, basically z would have become 1. Okay. And so in that case also, z becomes a real number. So if these two are not the cases, then we can simply cancel out 1 minus r e to the power I theta. And so finally we are getting this. And now we will use the theorem. So these three are collinear given. So then we have that this ratio will be a real number. So if this has to be a real number, then we get that this e to the power, so this is 1 by r, which is a real number, times e to the power minus I theta. Or you can just simply say that since this is a real number, so that implies r e to the power I theta has to be a real number, and which also implies that, so this is in r, which also implies that e to the power I theta is in r. Okay. And so what is e to the power I theta? That is cos theta plus I sin theta. So if this has to be in r, so that means this part has to vanish. And so that implies that theta is of the form some integer multiple of pi. Okay. And so since e to the power I theta is in r, so we have z to be equal to a real number. And thus, we are done. Thank you for watching. See you next time. Bye.